In this lecture, I'm going to cover the introduction to additive manufacturing, also known as AM or 3D printing. First, I will discuss the basic principle of additive manufacturing, the steps of additive manufacturing. Then, I will discuss different AM technologies or 3D printing technologies used in industry, the materials which are possible to process with these technologies, and the, the type of parts produced by these technologies. Then I will briefly discuss the current areas of application of additive manufacturing in industry. Let's go to the first slide. AM is an evolving technology, new processes, better machines, new materials are every day being added to AM industry. However, AM has already found vast range of applications, and industry is able to sustain high growth rates of around 30% already for some years. The current global AM industry's worth is estimated around 8 billion US dollars, which is expected to grow to 23 billion US dollars by 2026. So we are talking about an industry which is growing, and although it will not create a revolution in the industry, but will be still an important player, and it is interesting to learn about this technology. Initially, in 1990s, AM was used to produce prototypes for automotive industry. Subsequently, AM found its application for casting molds and tools. The continuous developments in AM allow to make end products, include the products which are very small or very complicated shape and not possible to produce with other technologies, or the numbers are very less, and it is better to not invest into the toolings, and because it requires a lot of capital investment. One big area or emerging area is the mass customization of products, like in jewelry or in medical field, especially in dental industry. Um, there are many products which are produced currently for dental industry based on the customized design for each patient. AM refers to the fabrication of parts by building up successive layers of formless material by an automated process based on digital 3D models. There is no requirement of dies and tools to fabricate the parts. Only you need is a 3D digital model. AM technologies vary from each other depending on the physical or chemical principles used to achieve solid bonds, joining techniques, or materials being processed. A typical AM process can be divided into three stages. Number one, data preparation. Number two, layer by layer building of parts. And then number three is the post processing of build parts. The stage one, data preparation, and stage three, post processing, are not automated at the moment and involve a manual experienced labor to perform the tasks. Let's go through these AM stages one by one. Stage one is data preparation, and this stage typically contains 8 steps. Step one is to create a 3D model. You can use CAD softwares which can create 3D models based on the part measurements. 3D scanners are also used to optically scan the parts, or in case of dentistry, these optical scanners are used to get the information from patient's mouth, and this information is used to create 3D models. In step 2, these 3D CAD models are converted into STL file format. This STL file format is a kind of de facto format for all the additive manufacturing machines. In this format, the surface of the parts is approximated by a mesh of triangles. This conversion can still contain some inconsistencies or defects. These errors are repaired in step 3 to have a consistently enclosed triangles with no errors. In step 4, this part is positioned in the build envelope, and in step 4, support structures are added to the part. Support structures are very crucial for for homogeneous building of the part. The part can have some overhang structures, and you need the support structures. However, these support structures shall be designed carefully, because it will require a lot of manual work to remove these support structures from the part, and it can also sometimes damage the part a bit. In step 6, this model is sliced into the parallel layers, which contains polyline contours, because STL in format have these models in only only from the surface. So those slices will contain the polylines of those contours. In step 7, these slices, those contours are filled. Actually, it gives a scheme how these slices will be filled. For example, in case of selective laser melting, hatching step actually defines what will be the process parameters, or the machine parameters filling the each layer. Like what will be the laser spot size, what will be the speed, what will be the hatching distances, what will be the scan strategies. So all these kind of parameters are specified at this stage. In step 8, finally the build is created, and you might still need to add some information, like which machine is being used, what is the process, either it is selective laser melting, or it is um, fused deposition modeling or stereolithography. So this kind of information is also added. What is the geometry of the part, and you might also have to fill in what kind of material is being processed. To help this data preparation stage, many softwares are available in the market, like Magic software, which is supplied by Materialize, is very famous all over the world. Um, 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 Quantum AM, supplied by Renisha, is also another example of the softwares used for data preparation, also known as build preparation. After data preparation, next stage is a part building stage, which is also called cyclic layer building. This is actually is a physical part of the AM process. I will take the example of selective laser melting to define this stage. Part building in case of selective laser melting starts with the spreading powder layer on the build plate with the help of a roller or a scraper. Then this build layer is locally melted by scanning with the laser according to the predefined geometries. When the whole layer is built, the build platform is lowered according to the predefined step, which is also known as layer thickness, and then another layer of the powder is spread, and the laser scanning process is repeated to build another layer, and this also step ensures that the current layer is bonded with the previous layer. Again, when the layer is complete, the platform is lowered, and another layer of powder is deposited, and laser scanning is repeated. So this process is repeated until we have a complete pot. Um, the layer thickness, or the step by which the build platform is lowered, is very critical. It also determines what will be the time required to build the build, and it also has influence on the mechanical properties of the parts. So there is always a trade-off between the quality and the build time when we define the layer thickness parameters. The next stage after part building is a post processing, and typically this stage involves removal of the parts from the build plate by removing the support structures. In some cases, like in stereolithography, it includes curing and washing and cleaning of the parts. For the metallic parts produced by selective laser melting or electron beam melting, you need to do also the heat treatment to remove the residual stresses in the parts, or to modify the microstructure, which has the influence on the mechanical properties. Hot isostatic pressing is also another kind of post processing applied to the metallic parts. This is uh, this eliminates the residual porosity in the metallic components. It also has the influence on the microstructure of the parts, and this is required when the parts are applied in critical applications, like in aerospace or in the case of medical implants, and the fatigue properties of the parts are very critical. Nowadays, some indirect printing techniques for metals and ceramics uh, are being industrialized, and these technologies use a binder material to build the parts, and this binder shall be debinded before the firing step to achieve high densities. Um, um, this AM process, or this AM methods have a lot of freedom to produce complex shape parts. However, the accuracy sometimes is not as required, and machining step is done to mill the parts according to the required dimensions, or for to achieve the required accuracy level. Sometimes the finishing of the surface is done to achieve the final surface finish levels. Let's go through the important AM technologies. First, we will talk about fused deposition modeling, FDM, also known as fused layer manufacturing or modeling, FLM. This technology comes under the category of extrusion-based technologies. This was launched in 1991, so roughly 30 years ago. It was patented by Scott Crump in 1989. The joining principle for the extruded lines or rods and the successive layers is based on adhesive bonding of hot melt. Um, Layer contouring is performed by extrusion of a plastic filament through a moving nozzle. So that moving nozzle contains or a heater, and this whole equipment is generally called extrusion head, and rollers are used to force the plastic filament into that head, where it is being molten because of a high temperature created by the heater. And the solid filament moving in with the help of rollers provides the pressure for the extrusion. ABS, PC, PLA, or mostly printed into the parts by using fuse deposition modeling. Nowadays, metals and ceramics are also produced by fuse deposition modeling. For metals and ceramics parts, instead of polymer filament, a composite filament is used which contains polymer and ceramic or metal particles. When that filament is extruded into a part, this part contains polymer contents and also metallic or ceramic contents. Polymer contents are removed by heating it to the higher temperature or dissolving into a soluble solvent, and in the next stage, the part is fired to higher temperature to increase the density of the part. Special features for FDM include that uh, mm, this technology has sold more systems than any other technology, AM technology. At this slide, another AM technology called 3D printing, also known as binder 3D printing, ZCOP, or voxel jet, is presented. This technology comes under the category of binder jetting. This technology was launched in 1993, also patented in 1993 by Massachusetts Institute of Technology. The joining principle for this technology is that the powder particles are bonded together by the help of a liquid binder. Um, Layer contouring is performed by depositing the binder in selectively depositing the binder on the powder layers. So it has some similarity with the selective laser melting, where the powder layers are bonded by local melting of the powder. But here that bonding is provided by liquid binder, which is also sprayed by print head. Gypsum, starch, PMMA, sand, or the generally the materials printed by this technology. Nowadays, this technology is getting some attention because the manufacturers are claiming that with this technology now you can produce the parts with a high density and better mechanical properties, which was not possible in the past. And with the improved properties of metallic and ceramic parts, this technology gives the advantage of the high productivity. Um, So nowadays there is some printers marketed or launched, and it is getting some attention. Um, Special features include that binders with the binder can be deposited by multiple nozzles, and this allows to print the objects with the colors. You can print ceramics or metallic parts. However, you will require a debinding and firing or sintering step. Another distinct feature of this technology is that you don't need support structures to build parts. Laminated object manufacturing is another technology which we are going to discuss now. This technology is also known as laminated object modeling or layer laminated manufacturing or sheet lamination. This technology comes under the category of layer lamination. This technology was launched in 1991, patented in 1987. In this technology, parts are built by gluing together different sections, which are separately cut with the help of a knife or a laser. Um, Parts of paper or adhesive materials or PVC can be printed by this technology. Special features. Um, um, Parts with the wood-like properties from the paper of different colors can be printed. Further, this technology doesn't require the sports structures, no, so not much of the post processing is required. At this slide, schematic of stereolithography process is shown. Stereolithography is an important and interesting additive manufacturing technology. It is also known as SLA or STL. It comes under the category of layer wet polymerization. This technology was launched in 1987 and was patented earlier in 1984. Parts are built in SLA by local polymerization of a photosensitive resin by exposure to ultraviolet light coming from a laser or an incoherent source of light. Thermosetting plastics like acrylic and epoxy resins are used to build parts in SLA. Interesting feature of SLA is that it can allow the fabrication of ceramic and metallic components with high density. This is achieved by stereolithography of a photosensitive resin which is saturated with ceramic or metallic particles. As build part is very comparable with injection molded part and requires a debinding and sintering step to achieve fully metallic or ceramic component with high density. Polyjet modeling, also known as object, is based on the material jetting. It was launched in 2000. Parts are produced in a typical polyjet modeling process by simultaneous jetting of photopolymers and UV curing. Um, Typically, acrylic and epoxy resins are printed using polyjet modeling. Polyjet modeling allows to print parts with different combinations and with the different mechanical properties. Recently, a company based in Israel, XJet, has launched a printer and materials which they claim can enable to print fully dense metal and ceramic parts with the high quality. Selective laser sintering, also known as polymer laser sintering, is a powder bed fusion based process. It was launched in 1992 and was patented earlier in 1986 by Carl Descartes. Parts in selective laser sintering are produced by uh, liquid phase sintering, which is achieved by local heating of polymer powder by CO2 laser beam. Um, Semi-crystalline thermoplastics, typically nylon, polyimide 12 or polyimide 11, or PEEK, are printed using selective laser sintering. A selective laser sintering process doesn't require the use of support structures. Selective laser melting is a very exciting additive manufacturing technology as it allows to print high quality metallic components. Selective laser melting is also known as direct metal laser sintering, laser cusing, laser metal fusion, direct metal printing, laser beam melting, and direct laser melting. So many names. It already shows how popular this technology is. This technology comes under the category of powder bed fusion processes. It was launched in 1999 and was patented in 1996. Parts in selective laser melting are produced by local melting of powder layers by a laser beam. Almost all the weldable metals can be used in powder form to produce metal components. This is a very important technology, and it is at the moment most commercialized or industrially applied technology to produce 3D printed metallic components. So, in incoming lectures, I will discuss selective laser melting process in detail, the materials properties, um, as in powder form, critical to produce high quality components, post processing, heat treatment, hipping, and effect of um, the SLM process parameters and post processing on final parts, mechanical properties. I will cover all these topics in coming lectures. Electron beam melting is also very exciting technology to produce metallic components. After SLM, which we discussed on the previous slide, electron beam melting is most widely applied technology. Similar to selective laser melting, it is also a powder bed fusion process which was patented in 2004. The basic difference between EBM and SLM is a heating source. So in EBM, electron beam is used instead of laser beam to produce local melting in powder layers. Similar to SLM, all the weldable metals can be printed into metallic components. The parts produced by EBM can have different microstructure and mechanical properties from selective laser melted components. And in coming lectures, we will cover the differences between EBM build parts and SLM build parts. Laser metal deposition is another interesting AM technology to produce metallic components. This technology is also known as direct metal deposition. laser engineered, net shipping, electron beam additive manufacturing. As you can see from the name, this technology comes under the category of direct energy deposition. This technology was launched in 1997. Metallic components are produced by this technology by depositing the beads of the material from a processing head. This processing head has the ability to deposit the material in the form of powder or wire, and the heat from a source of laser or electron beam. Almost all the weldable metals and alloys can be produced by this technology. However, currently this technology is most applied to produce the parts of high temperature alloys like inconel alloys. It's also being investigated to produce TI-64 parts. This technology is also more suitable for the large scale parts. After discussing the key additive manufacturing technologies, let's go through current established areas of application for additive manufacturing. Generally, areas of application for AM can be divided into four categories: prototyping, fabrication of models and molds, fixtures, template and drill jigs, and number four is manufacture of end products. Let's go through one by one. Prototyping. Prototyping is one of the earliest applications of additive manufacturing and is now has become quite essential in the area of prototyping. The extremely short lead times of AM are a very important benefit in prototyping, whereas high cost is an acceptable trade-off. Prototypes can be divided into concept or visualization of models. The function of this prototype is purely of aesthetic function. The other is geometric prototypes, and these prototypes are produced for fitting simulations. The other type is function prototypes. These prototypes are used to perform the individual functions of individual products. Technical prototypes differ from the final product only in the way they are produced. Concept or visualization of model can be achieved by a 3D print technology, laminate object manufacturing, stereolithography, polyjet molding, or fused deposition molding technologies. Geometric prototypes can be produced by FDM, PGM, SLA, or SLS. Functional prototypes are generally produced by selective laser sintering or FDM or SLM, whereas technical prototypes are generally produced using selective laser melting or electron beam melting. Fabrication of models and molds is another established area for additive manufacturing technology. Initially, AM was used to produce models which were a replica of the part to be manufactured. These models were used to make molds of sand or silicone, and then these molds were used to fabricate the final parts. The advancements in 3D printing or additive manufacturing of metals has now enabled to manufacture the molds, metal mold itself. The the advantage of using additive manufacturing technology is that you can create conformal cooling channels into the molds, which help to achieve high cooling rates and also increase the life of molds. Fabrication of fixtures, templates, and drilling jigs for customized application is another interesting area of application for additive manufacturing technologies. Let's take the example of surgical guides used during dental implant surgery. These guides are designed based on the data coming from patient's mouth from a cone beam X-ray CT scan. These devices are then printed, generally using a stereolithography printer. These devices help for a smooth surgery. Based on the similar principle, guides for knee surgery and shoulder surgeries are also fabricated. A few years back, additive manufacturing technologies were only able to produce parts for prototyping or short-term applications. However, continuous improvements in additive manufacturing technology processes, especially selective laser melting, has enabled to use additive manufacturing technology to produce high quality functional components for long-term use. The parts produced by SLM are as good as the parts produced by conventional manufacturing technologies like casting or machining. For example, in medical industry, cobalt chromium and Ti64 denture frameworks and superstructures are one example where the end user medical devices are produced based on customized designs. Water pump wheel for motorsport industry are produced by selective laser melting. Fuel nozzles for LEAP engine are produced by General Electric, or the example of certified serial production for the long-term applications. So that's all for this lecture, and if you have any questions, please leave it in the comments on the video.